Hello and welcome to this tutorial on week 2 contents of Machine Learning Foundations course. In this tutorial, we would be solving some problems from the topics linear approximation, higher order approximations, multivariate linear approximation, and directional derivatives. Let's start with linear approximation. It's also called linearization or local linear approximation or tangent line approximation as well. The idea behind linear approximation is that when we zoom in on a point on a nonlinear plot, it looks very similar to a straight line. So we can use the equation of the tangent line at a point, say A, to approximate the value of the function at other points that are near to this point A. Let's take a look at an illustration. This blue plot is the plot of the function sin x, and this red straight line is a tangent on this function at point A. Now, the idea here is that we can use the equation of this straight line, of this tangent line, to approximate the value of the function at points which are near to this point A. As long as we are near this point A, we will be able to approximate well and the error will be small, as you can see here. But as we move away from this point A, the error increases and we will not be able to approximate well. So that's the main idea behind linear approximation, that we'll approximate the value of the function which is non-linear by using the equation of the tangent line at a given point A. And all those points that are near to this point A will be able to get a good approximation, but not for the points which are far away from this point A. Now getting back, what is the need for linear approximation? So firstly, linear functions are easier to work with. That is why approximation is an important process in engineering and experimental sciences. In scientific studies, for example, if you're building a model, then linear functions help in making those models simpler and make the calculations easier. Now the second use is we can use linear approximation to find the value of a function at certain points when the exact values are not known. As an example, let's say you don't have a calculator and you want to find out the value of, say, square root 5. Now, since you know the value of square root 4, you can use it to compute the value of square root of 5. So that's a very basic example. We'll take more examples in a while. And this is the equation that we'll be using to approximate given function f of x. Let's say the linear approximation is represented by L of x. So the entities that we need would be the value of the function at point A and the value of the slope of the function at point A, that is f prime A. So these are the two things that we would be needing. Now if you observe carefully, this is actually the equation of a straight line at the points A comma f of A. So you see, this is the equation of a straight line which passes through the points x1 comma y1, and m is the slope of the straight line. Now if you replace x1 comma y1 by the point a comma f of a, because this straight line is passing through the point A, so we can replace x1 comma y1 by a comma f of a, and the slope m can be replaced by f prime a. So this is what we get, and this is indeed the equation of the linear approximation of the function f of x at point A. Now we'll use this equation to solve some problems. Let's say we have to approximate the value of square root of 50. So the first step is to find a point A which is near to this point at which we need to find the value of the function. So here you see the function is of the form square root of x, and x is equal to 50 is what we need to find out. So we will find a point A which is near to this point x where we know the value already. So as an example here, we know that square root 49 is known. So we will use A is equal to 49 to approximate the value of the function fx is equal to square root x to compute f of x at x is equal to 50, right? So that's the objective. So the first thing that we need is f prime of x. We compute f prime of x and then we replace f of x and f prime of x by a is equal to 49. So these are the two things that we need. We would be putting these values in the equation. So we get the linear approximation of the function L of x is equal to f of 49 plus f prime of 49 into x minus 49. Because here a is equal to 49, so we replace the appropriate values, and this is the equation of the straight line that we get. So you see, this is a linear function L of x, which we would be using to approximate the given function f of x is equal to square root of x. Now looking at the plots, you see this blue plot is representing the function f of x, and this red straight line is the tangent, which at the points near a is equal to 49, it's able to approximate the given function well, right? So that's how we can use this straight line to compute the value of the function near 49. So let's see, when we put x is equal to 50 into this equation, what is the value that we get? That's 7.071 that we get. Now, if you see the exact value of square root 50 up to 3 decimal places, that also comes out to be 7.071. So as you can see, this was a non-linear function, and we used an equation of a straight line to compute the value of this function, and we are able to approximate it decently well up to 3 decimal places. Okay, so that's the main idea uh, of linear approximation. Now let's see what happens when we use this equation to find the value of the function at points away from a. As an example, if you put x is equal to 100, which is too far away from this point a, this straight line would be giving us some value, but there would be this gap, as you can see, the gap between the red line and the blue plot. So that gap will be the difference between the actual value and the approximated value. So when we use this equation, we get 10.64, but the actual value is 10. So we get some gap. That's because we are moving far away from this point A. Let's take a look at one more example. We need to approximate the value of e to the 0.017. Now here again we would see a value which is close to this value and is well known. So as an example, e to the 0 is known. So what we can do is we can form the function of function fx to be of the form e to the x while putting the value of a is equal to 0. So we get f of x to be equal to e to the x, and then what else we need is f prime x is equal to e to the x again. Now we replace fx and f prime x by x is equal to a, which is 0 here. So these are the two things that we get, and we put these values in the equation as usual, f of a plus f prime of a into x minus a. Now when we replace the values, the straight line equation that we get is 1 plus x. Now this plot represents how the straight line is approximating this function at the point a is equal to 0, right? You can see that from this place to this place, this equation is able to approximate the function well. So what we need is e to the 0.017. So we replace x by 0.017 and we get 1.017, right? And when we see the actual value of e to the 0.017, that is also same. So we are able to approximate quite well up to 3 decimal places by using the equation of the straight line. Now again, if we go far away from this point 0, there would be some difference between the approximated value and the actual value. Let's say we put x is equal to 1. So L of 1 will give us 2, while the actual value is 2.718. So that's the gap that we obtain. That's because there is a difference between 0 and 1 as compared to the gap between 0 and 0.017. So if we stay near 0, we'll be able to approximate well. Now let's see one more example on linear approximation. So here we are given f of x is equal to square root of x plus 4, and we need to find f of 6. So when we replace x by 6, we get square root of 10. So square root of 10 is what we have to compute. Now as usual, we would see a value close to square root of 10, which is already known, and that is square root of 9, which we know already. So square root of 9 makes a to be equal to 5, right? So fx is given and a becomes 5, and that's how we start. And then we compute f prime of x that we need to get the approximation. And then we replace x by 5, a is equal to 5. So these are the two entities that we get, and then we replace these values in the equation of linear approximation, and this is what we get. So this is the straight line equation that we get, 3 plus x minus 5 divided by 6. this was a non-linear function and we get a linear function, linear approximation represented by this red straight line, and you see that this is able to approximate to well in a local region. So as long as we are near this point 5, we can use this equation. Now what we need to compute is f of 6. So we replace x by 6 and use this equation. Let's see what we get. What we get is 3.16666, and if you see what is the exact value of square root of 10, that is equal to 3.1622. So you see there is some small amount of gap, so it is exactly matching when we see up to two decimal places, but when we go beyond, there is some gap that we observe, and that is because there is a gap between 5 and 6, right? If you use this equation to compute value somewhere uh, very near to 5, say 5.1, 5.2, you would get a good approximation. Now can we make it better? So next topic is about, can we make this approximation a little better? Now let's talk about higher order approximations. Now, as you see here, a nonlinear function was given, and we were always coming up with a linear straight line equation to approximate that function. When we go one step ahead, we can also come up with the quadratic approximation as compared to a linear approximation, or we can go even beyond and we get even higher order approximation. So that is also possible. Now let's take a look at the equation that we would require to obtain that. So this is a linear approximation equation. We now add one more entity to this equation to get the quadratic approximation, where we need the value of f double prime a, and we will get a second degree term over here. Similarly, if you go beyond, we can get higher order approximations, and by adding more terms containing higher degree derivatives and higher degree terms, so we can go as far as we wish to get a little better approximation. Now, what we'll do is we'll take the same problem that we took in the previous example, and we'll apply a higher order approximation to that and see how better approximation we are able to obtain. So this is the same problem. Earlier we had applied the linear approximation and we obtained some value where there was a little gap between the actual and approximated value. So now we apply a say third order approximation here and see what we obtain. We put a to be equal to 5. Now instead of f prime x, we also need higher order terms of the derivatives. So let's compute the approximation up to third order. So these are the three terms that we would be needing, and then we replace x by a, and these are the terms that we would be putting in the formula. So linear approximation of x becomes f of 5 plus f prime of 5 multiplied by x minus 5 plus f double prime of 5 divided by 2 multiplied by x minus 5 square plus f triple prime 5 divided by 3 into 2 multiplied by x minus 5 cube. So we are computing up to third order approximation. So we stop here uh, and we replace all the values, and this is what we get. So this is the equation of the approximation. This is not a linear approximation, this is a higher order approximation. Now we'll see how better we get when we use this equation as compared to the linear equation that we used in the previous example. So this is what we get. This blue plot is as usual the function f of x, and this red line is now not a linear straight line. It's a third order function, and we see that this function is able to approximate the given function better in a farther range. So when we compute the value of f of 6 by using this equation, we get a value 3.1622, and this was the exact value of the function up to 4 decimal places as well. So we are able to match this value with the exact value by using a higher order approximation. Now let's move on the next topic, multivariate linear approximation. So far the functions that we were dealing with had only one variable, but sometimes we deal with functions involving more number of variables. So how can we approximate those functions is what we will look at. This is just a generalization of that equation that we used earlier. Now here the function f contains two variables x and y. So we need to find the linear approximation of the function in the vicinity of the point a comma b, which is equal to f of a comma b plus dou f by dou x of a comma b multiplied by x minus a plus dou f by dou y of a comma b multiplied by y minus b. You know that when we have to find the derivative of function which involves more than one variable, what we actually compute are the partial derivatives. So that's what we are using here instead of the term f prime of x. What we use is dou f by dou x and dou f by dou y. So this was a linear approximation of a multivariate function. You can also go one step ahead and you can get a higher order approximation of a multivariate function as well, as we did in the previous case. Now here we'll take some examples of linear approximation of multivariate functions. Here the function is x into e to the xy. We need to find the linearization of this function at the point 1 comma 0, and then we'll use that equation to approximate the value of the function f at point 1.1 comma minus 0.1. Now as 1.1 comma minus 0.1 is in the vicinity of the point 1 comma 0, so we can use the approximation equation to compute the value of this function here. So what are the terms that we need? We first need to compute the partial derivatives of the function at x and y. So dou f by dou x is what we need, and dou f by dou y. And then here the point a comma b is equal to 1 comma 0. So we replace these values in the partial derivatives. So these are the two terms that we get. Now we need to replace these values in the equation of linear approximation. So f of 1 comma 0 plus dou f by dou x of 1 comma 0 multiplied by x minus 1 plus dou f by dou y of 1 comma 0 multiplied by y minus 0, because a comma b is equal to 1 comma 0. So this is the equation and we replace the values, and this is the linear equation that we get. So now what we need to compute is f of 1.1 comma minus 0.1. We replace the values in x plus y equation, and what we get is 1. So this is the approximated value of the function at this point. Now let's see what is the exact value of the function that we compute, and we find it to be 0.98542. So there is only a very little gap between the actual and approximated value, which means we were able to approximate decently well by using this equation. So that was about approximations, and now the topic that we look at is directional derivatives. You might already be familiar with the partial derivatives. So what are partial derivatives? If there is a function f of x comma y, then fx x comma y, or also called dou f by dou x of x comma y, what is it that it actually represents? It represents the rate of change of the function f with respect to x by keeping y constant, right? Now what do you mean by keeping y constant? So if you visualize, by keeping y constant, we are actually moving in a horizontal direction. We are finding the rate of change of the function in a horizontal direction, right? So this is the rate of change of f as we vary x by keeping y fixed. Similarly, if you look at dou f by dou y of x comma y, that is equal to rate of change of f with respect to y, where we keep x constant. Now, when we keep x constant, that actually means we are moving in a vertical direction, right? So that's what it is. But sometimes we might want to change both of these variables, and we would want to see what is the rate of change of the function f when we change both x and y. So we might want to find the rate of change of a function in a given direction. So that's what exactly is directional derivative. It's the rate of change of f if we allow both x and y to change simultaneously in some direction u. So this u is a unit vector that represents the direction in which we want to compute the derivative. Now let me give you a small example here. Assume there is a huge hill on which you are hiking, and there is a road spiraling around this hill which is making you reach on the top of the hill. So while you are hiking along this road, at some point, say you want to know what is the slope of the hill along this road, right? That's you might be interested in finding that. Or in another scenario, you might throw some ball down the hill, and you might want to know the slope of the hill in that direction, in the direction where this ball goes. So these are two different directions. One is the direction where this ball goes downhill, and the second is the direction along which you are walking on this road. So these are two different directions. So standing at the same point, you are interested in finding the slope in two different directions. So that's one scenario where directional derivatives might be useful. So let's see how we compute them. So they are indeed the weighted sum of partial derivatives. So this is partial derivatives, and this u vector is giving you the direction in which you want to compute the directional derivatives. So this is what you get, which is actually a weighted sum of the partial derivatives. Let's take an example. You're given a function f of x comma y, and you want to compute the derivative of this function in the direction of a vector that is given to you. So the terms that we need to compute this is first are firstly the partial derivatives, dou f by dou x and dou f by dou y. Now, secondly, we need a unit vector in the direction in which we want to compute the directional derivative. So this is not a unit vector, so we will first convert it into a unit vector by dividing each term by the magnitude of this vector. Next, we compute the directional derivative as a weighted sum of the partial derivatives. So this is what we get. So that's how we compute the directional derivatives. We'll take one more example and we'll conclude. So here in this problem, we are given a function and we are given a direction, and we are also given a point at which we want to compute the directional derivative. So as usual, first we'll compute the partial derivatives, dou f by dou x and dou f by dou y. Now for the direction, we are already given a unit vector, so we don't need to convert it into any other form. So to compute the directional derivative, we find the weighted sum of the partial derivatives. So this is what we get as the directional derivative of the function in this direction. Now we have to compute it at a given point 2 comma minus 3. So we replace x and y by this point, and this is what we get. So this is the rate of change of the function when we move zero point 0.6 in x direction and zero point 0.8 in y direction. So that's what it precisely represents. So this is how you can compute how much a function varies in a given direction at any point. So that's going to be a very useful concept which we might be using in future. Okay, so these were some of the example problems on the topics that were covered in the lecture. I hope you were able to understand. Thank you.